Welcome to Positive Physics. Today we're looking at logarithms. So we're going to understand the orders of magnitude and the logarithmic scale, to use logarithms for simple calculations, to learn and use the logarithm rules, and to understand why and when we use logarithms in physics. So orders of magnitude. If I asked you to plot on a linear scale the following: the radius of a proton, radius of a virus, height of a human, radius of the Earth, Earth-Sun distance, radius of the solar system, distance to the nearest star, you'd think I was losing it a bit. Because how can you plot something that is something times 10 to the minus 15 on the same scale as the radius of the solar system? Is it impossible? How about on a scale like this? So I've done a small section here. If we used 10 to the minus 15, 10 to the minus 14, etc., then actually on that particular bit of scale there, we would have the radius of a proton and the radius of a virus, about 10 to the minus 7, being quite close together on our scale. So this is called a logarithmic scale. If we're increasing in orders of magnitude, then we can represent really different distances on the same scale. It's very useful when we're looking at distances in the solar system, and more particularly when looking at distances within and between galaxies, which is something that you will do when you come onto your astrophysics and cosmology sections of the course. So what is a logarithm, or log? That's that button on the calculator that you've not used yet. So the logarithm of a number converts the number to an order of magnitude scale. So we can have a logarithm with base 10 tells you the power that 10 has been raised to give that number. So we see written here, logarithm to base 10 of the number y equals x. But I expect you're still thinking, what does that mean? The small number tells you the base, more on that. X is the power that 10 is raised to, that's the exponent. And here, y is equal to 10 to the power of x. Perhaps it's starting to clarify. Thinking about the number 1000, how many different ways can we write it? Don't mention words, I'm thinking numbers here, guys. So, 1000, that's the same as 10 times 10 times 10. Or if I was going to write it as a power relationship, 10 cubed, 10 to the power of 3. 3 being the exponent, what 10 has been raised to get the number 1000. So when I write log to the base 10 of 1000, it equals 3. In other words, 10 to the power of 3 equals 1000. On your calculator, you've got a log button, and that's always to base 10. Wherever you see log with no base number, you can assume it is base 10. But there are other bases. How many ways are there of expressing how many 2's we can multiply to make 8? So again, same thing. 2 by 2 by 2 is 8. 3 2's, or 2 to the power of 3 equals 8. 3 being our exponent again. Or log to the base 2 of 8 is 3. That's expressing it as a logarithm. The number of 2's we need to multiply to get 8 is 3. Therefore, the logarithm is 3. An example calculation then. Log to the base 3 of 27 is 3. Why? Because 3 cubed is 3 times 3 times 3, which is 27. What about the following? Log to the base 10 of 15. We need a calculator. Well, I certainly do. So log to the base 10 of 15, and notice I've no longer put the little 10 here now because we're assuming its base 10 is 1.18 when we put those numbers in our calculator. Taking logs and raising 10 to the power of x are inverse functions. So what it means is that 10 to the power of 1.18 is 15. Now there are some rules we need to follow when using logarithms. So far, we've got 10 to the power of log x equals x, and log of 10 to the power of x equals x. If you look back over what we've just done, then you'll see how that works. Useful logs to remember though, log of 10 is 1. 10 to the power of 1 is 10. And log of 1 is 0. That's true because any number raised to the power of 0 is 1. So if I raise 10 to the power of 0, it's 1. If I raise 2 to the power of 0, it's 1. If I raise 30 to the power of 0, it's 1. Now, here we come into some different rules. Log of x times y is equal to log of x plus log of y. So if we were given a function where we had log of two numbers multiplied together, we know that we can just separate out that particular function there into log x plus log y. Likewise, log of x divided by y is log of x minus log of y. And log of x to the power k is the same as k times log x. You do need to know these rules, and you will need to be able to recall them when you're rearranging equations and using logs in your physics A-level. Now, natural logs. Some of you may have heard of them, or you may spot as you were looking at your calculator at the log button, this little button ln. That's for natural logs. And natural logs are to the base e rather than base 10, where e is Euler's number. Now, you can look that one up. If you're doing maths, further maths, you may have already done that in your maths studies. If not, go away and find out where Euler's number comes from. You don't need to know it for your physics A-level, but you might want to extend your knowledge. E is equal to 2.71828. You don't need to remember that. It's in your calculator. So natural logs are used when the rate of change of a quantity is proportional to its size. This tends to happen in nature. For example, from GCSE, you know that the rate of radioactive decay is proportional to the number of undecayed nuclei in a sample. Honestly, you do know that. You know that there is a constant half-life when an active sample decays, and that the activity readings when we're looking at the decay of a sample are based on how many samples of the nuclei we started off with, how many have already decayed and how many are left to decay. I may have just expressed it in the A-level wording. So equations using base E then that you might find, and we'll look later into how to manipulate these equations, but generally they take the form A equals A naught e to the minus lambda t, or some other constant here. You can get n equals n naught e to the minus lambda t. This is the equation for radioactive decay, where A is the activity, A naught is the initial activity, A activity after time t, here's your time t, and lambda is the decay constant, which is specific for a particular material. Now, written E, when we write it like this, please don't confuse it with the fundamental charge when it's written in an equation. It is not 1.6 times 10 to the minus 19. It is E, Euler's number, and you should be using it as the inverse of the natural log if you were using E raised to this power. So just be careful not to fall into that trap. So here we have natural log of 250. All we need to do to answer that question is use our calculator and using the ln button, and you should find that natural log of 250 is 5.52. How would we answer these questions though to find x and y? Log of x equals 3.6, or natural log of y is 0.31. It's the inverse function on your calculator. So, log of x is 3.6 is the same as 10 to the power of 3.6, which equals 3,980. And natural log of y is 0.31. That's the same as e 0 to the 0.31, which is 1.36. So the natural log rules look remarkably familiar to log rules. We've got e to the power of natural log of x is equal to x, and the natural log of e to the x is x. And our useful logs to remember are natural log of e is 1 and natural log of 1 is 0. We have the same rules though when we're combining products. So natural log of x times y is the natural log of x plus the natural log of y. The natural log of x divided by y is the natural log of x minus the natural log of y. And the natural log of x to the k is equal to k times the natural log of x. They're very familiar, they're just the same, and the good news is once we've learned them for logs, we've learnt them for natural logs as well. So what about this question here? Log to the base 2 of 8,388,608. Don't panic, firstly, this is extension work. It requires you to use a log with 2 as the base, which isn't preset on your calculator, so you'll need to convert from log 10 to log 2. But you can do so using this equation. Log to the base a of x is equal to log of x, which is in base 10, divided by log of a in base 10 as well. So if you're fancy, you may have the ability to set your own logs on your calculator. But let's have a look. So we've got this equation, log to the base a of x is log of x over log a. So for example, if we had log to the base 2 of 8 was x, x would equal log of 8, which is our x part here, divided by the log of 2, which is a there, and that equals 3. Now you have a go at the tricky one. And good luck with logarithms.